Good morning, everyone. In the last class, what we studied, everyone can see the desktop. Yeah. In the last class, we studied about switch debouncer. I said about the mechanical switch and the problem what we have, the contact bounce problem what we have with the mechanical switch. I said about because of the springness of the switch, what will happen is it keeps switching between the positions there. So that what we have is we have this issue, right? In order to avoid the contact bounce problem what we have with the mechanical switch, we are using an SR latch. With the help of the SR latch, what we made sure is we made sure that it is at logic 1 and this is at logic 0 here, right? I explained about how this circuit is working with the help of SR flip-flop latch here. And next, we studied about master-slave flip-flop. I explained you why there is a need for master-slave flip-flops. Anyone can explain me what is the reason for using the master-slave flip-flops as we discussed in the last class? Anyone? What is the reason for using the master-slave flip-flop? I said with respect to latches, how the latches work, as and when you give the input, the output will be impacted immediately, like depending on the enabled signal, right? Also, I said that with the drawback what we have, or the limitation what we have with the clock pulse, right? When the flip-flops are dependent on the clock pulse. I explained about one condition when J and K inputs are equal to logic 1, right? Equal to 1, and the clock input is 1, right? And we assume that the clock pulse is is logic 1 for a long period of time. What will happen is when the J input and the K input both are logic high, what will happen is the output will keep switching from 1 to 0, 0 to 1. The output will keep switching, will start toggling, right? There is uncertainty in the output of the flip-flops there because it keeps on toggling between zeros and ones to zeros. That is the issue what we have when the flip-flops are dependent on the clock pulse, right? I explained that when the propagation delay of the flip-flops is less than the width of the clock pulse, we have this condition, and this condition we call it as a race around condition. Everyone note down this one. This is called as a race around condition, right? In order to avoid, to overcome this one, I said the one of the restrictions what we can have on the design is the propagation delay should be greater than the width of the clock pulse. That is a restriction what we can have so that we don't have this race around condition. And the best way to deal with this issue is dealing with two different categories of flip-flops. What are those two different categories of flip-flops we have? One is the master slave flip-flops, which is also called as a pulse triggered flip-flops. The other one is the edge triggered flip-flops. In master slave flip-flop, we studied about an SR flip-flop. What do you mean by master slave flip-flop? Anyone? What do you understand by master and slave section here? Anyone? Rohit, Jyoti, Suti, anyone is there? Kavya? What do you mean by master slave? As I said, when I say master slave flip flop, we have it is nothing but a cascaded connection of a master section and a slave section. What we have it here, right? We know about how the SR latch works. We studied of the function table. If you see this one for a master and slave section, as you see here, the difference what you can see is in the clock, right? We have an inverter, and the output of the inverter is given to the clock of the slave section here, right? Now I explained about this, the clock pulse here, and as I said here, right, during the rising edge of the clock pulse, what will happen is the master will be enabled and the slave will be disabled, so that whatever the input you have, the switching of the inputs will take during the rising edge of the clock pulse here. Just a minute. I'm just trying to get the annotation laser. As I said here, for this one, as explained with this one here, during the rising edge of the clock pulse, what will happen is the master is enabled and the slave is disabled, right? And also there is a section of time, right, where both the master and the slave are disabled, right? The one important point what you should remember with respect to master slave clock is that, right, if you see this one, as I said, during the rising edge, right, the master is enabled. When I say the master is enabled, it means that the switching of the inputs takes place during the rising edge. It means that the whatever input you have given to the master section, that is given to that input is given to the master section, so that depending on the input combination what you given to the master section, the outputs of the masters will be generated during this master rising edge. What I'm trying to say is that the switching of the information, the whatever the input information you give to the master, right, that takes place during the rising edge. That information is given to the master section. And during the falling edge what we have for a clock pulse, right, this is where the slave is enabled and the master is disabled. During this time, what will happen is that, right, the output of the slave will be generated. It means that with the same clock input, the switching of the input information as well as change in the output information also takes place. It means that this during the rising edge, the input information is given to the master section. During the falling edge of the clock pulse, the slave output will be generated, right? That is how the master slave flip-flops work here, right? And also, one important point, as I said, for the operation of the master slave flip-flop, always there has to be a time period where both the master and the slave both should be disabled here, right? I explained about this one in detail in the previous class, right? Any doubts you have with this understanding, anyone? Please let me know. I'll explain the JK flip-flop. If you have any doubts, like, I'll try to emphasize there, so that if you have any question, you can ask me at the end of the class there. Right? I explained about this timing diagram of an SR master slave flip-flop, right? And this is the truth table of a master slave SR flip-flop, and this is the clock pulse which is applied. We know that when it is 0 0, the next state is equal to the previous state, right? The next state is equal to the previous state. And 0 and 1, when R is 1, we call it as a reset state. Reset state means the output is equal to 0. Irrespective of the previous state, if R is 1 and S is 0, the output will always be equal to 0. Next, when S is 1 and R is 0 and the clock input is applied, right, irrespective of the previous state, the output will always be logic high here, right? And 1 1, what we call it as an undefined state, R, right? Indeterminate state here, right? This state is not used. We are not supposed to apply this S and R as 1 simultaneously here. As I said, when the clock input is 0 here, irrespective of the input S and R here, the next state is always equal to the previous state here. And the logical symbol for the master slave SR flip-flop is shown in the diagrams here. Right? You can see the bubble is nothing but it shows that Q bar. Next, what we have is master slave JK flip-flop. Right? As I said here, when I say master slave flip-flop, it is nothing but a cascaded connection of a master section and a slave section, right? And when I say master slave, in the output of the inverter, right, which is the clock input what we have, right, the output of that inverter is given as in clock pulse, clock input to the slave section, right? And also you can see that there is a feedback from output to the input, or as you can see from this diagram here. What we have is a J input. Just a minute, I'm trying to open the annotation. This is J input, K input, and the clock pulse what we have here. And J is nothing but it is given as in yes. It is nothing but yes. K is nothing but R. S is a set state and R is the reset state or the clear state what we have it. As I said here, how it works here, during the rising edge, whatever the information what we have here, right, that is given to the master section, and during the falling edge, right, depending on the input what we have, the outputs of the slave section will be generated. It means that during a single clock pulse, the switching of input information as well as the output of the slave section is also generated during the same single clock pulse. Right? That is how the master slave section works here. As I said here, as you can see, the JK flip-flop what we have is nothing but the improved version of the SR flip-flop. We know that for SR flip-flop, we cannot have S is equal to 1 and R is equal to 1 simultaneously, because that is an indeterminate state, undeterminate. Like as I said here, the output is, we are unable to predict the output state when S and R is equal to 1 simultaneously, right? But in JK flip-flop, we have that state defined here in a JK flip-flop. Yeah, you can see, everyone can see this, the function table of a master slave JK flip-flop. This, as I said, this is similar to the SR flip-flop. This is nothing but yes, and this is nothing but R here, right? When J and K are 0, 0, the next state is equal to the previous state, right? If the previous state is 0, the next state is also 0. If the previous state is 1, the next state is 1 here, right? Similarly, when J is 0, K is 1. As I said here, this is similar to the R what we have in a SR flip-flop. It is nothing but a reset state. When I say reset state, what to understand by that? Irrespective of the previous state, the next state is equal to 0. If the previous state is 0, the next state is also 0, right? If the previous state is 1, the next state is also equal to 1. Irrespective of the previous state, the next state is always equal to 0. If K input is 1, J input is 0. And similarly, what we have, J is 1, K is 0. When J is 1, K is 0, as I said, this is nothing but its set state. Irrespective of the previous state, the output of this will be 1. Similarly, what we have when both J and K are 1. As I said, with respect to SR flip-flop, when both S and R is 1, we called it as an undefined state. It means that we cannot have both S and R as logic 1 simultaneously, because the output is unpredictable, right, in SR flip-flop. But in JK flip-flop, what we have a defined state. What it says is that when both J and K are 1, the next state is nothing but the complement of the previous state. Complement of the previous state. Assume that the previous state what we have it here, right, and this is the next state what we have, and we have J and K here, right. When both are 1 1, assume that this is the previous state. The previous state is 0 here, right. And what is the next state here? Next state is nothing but the complement of the previous state. As I said here, it is nothing but Q bar. What is the previous state? We have 0. So that what is the complement of the previous state? It is 1. If the previous state is 1, right, as I said, the next state is equal to the complement of the previous state. So that what will be the next state? It is equal to 0, right. Here we have a defined state when J and K is equal to logic 1 simultaneously. Everyone understood this one? That is the difference what we have with respect to the SR flip-flop. And this is the logic diagram for a master slave JK flip-flop here. And this is the timing diagram of a master slave JK flip-flop. If you see, this is similar to the what we studied for SR flip-flop. The only difference what we have is during when both J and K are 1 here, right? When both J and K are 1 and the clock is high there, what will happen here? The next state is equal to the previous state here, right? The next state is equal to the previous state. That's the only difference what we have in the timing diagram with respect to JK flip-flop, right? We know how the master works. As I said here, during the master, when during the rising edge here, what will happen? J is 1, the K is 0. What will happen? This is high. The master section will be high. This is QM bar. This will be low, right? You always look for QM and QS here, right? And during the falling edge, what will happen here? We have this is 1 and the QS bar is 0 here. Any confusion in understanding master slave JK flip-flop and master slave SR flip-flop? As I said here, the difference what we have in JK flip-flop is we have a defined state when both J and K is equal to 1 simultaneously. But with respect to SR, we cannot apply both S and R as logic 1 simultaneously because it is an undefined state, because the output is unpredictable there. Okay, now we'll go to the next additional master slave flip-flops. The next master slave flip-flop is D flip-flop. What is this? D stands for? Anyone? What is this D? Jyoti Patil, what is D stands for?
Diode, sir.
It's a diode. Huh? I said it's D stands for data. Why it is called as data? Because whatever the input information you give to D, that is given as an output. If the D input is 0, the output will be 0. If the D input is 1, the output will be 1. So that whatever the input information you give, the same you get as an output. That is called as a D. D stands for data. As I said here, this is 0 here. So that what is we have? This is S is 0, R is 1. When R is 1, what you understand by this one? It is nothing but reset state. When is reset state? This is 0, this is 1, right? Similarly, when D is 1, S is nothing but 1. Since inverter output is given to R, this will be 0. Now S is set state. S is 1, R is 0. So that output is 1 here. This will be 0. So that whatever input information you give, you get that as an output. When this is 0, as I said here, this is 0. The output will be 0. Right? This is called as a data flip-flop or a D flip-flop here. And the logic symbol for this is shown in the diagram. We have a clock pulse, we have D, this is Q and Q bar here. I already explained about the D flip-flop. Everyone can see the diagram here. With respect to latch, explained of the function table, right? Everyone can see this one. When D, we have a clock input, Q plus, right? This has to be bar, Q plus bar here. Everyone make that change here. When it is 0, the clock input is applied, the next state is equal to the 0 here. When D is 1, when the clock input is applied, it is equal to 1. And when the clock input is 0, irrespective of whether D is 0 or 1, the next state is always equal to the previous state. This is about the master slave D flip-flop. Next, what we have is a master slave T flip-flop. If you see this one, right, what do you mean by T flip-flop? And T flip-flop, as I said here, is obtained by tying the input terminals J and K of the master slave flip-flops. Right? What we have is the J and K inputs are tied together. This is nothing but my T input, and T stands for toggle. T stands for toggle here. As you can see from the function table for this one. If you see the function table for this toggle flip-flop or T flip-flop here, when it is 0, when the clock input is applied here, when T is 0, the next state is equal to the previous state, right? There is no change in the next state when the T input is 0, right? As you can see from this one. Similarly, what we have when T is 1, when the clock input is applied, the next state is equal to the nothing but the complement of the previous state here, right? And when the clock input is not applied, irrespective of whether the T is 0 or 1, the next state is always equal to the previous state here, right? Right? If you can see from this one, when T input is 0, when T is 0, we know that, as I said here, and T is 0, what will happen? As I said here, the same information is given to the J and K input terminals. When J and K is 0, what you understand by this is nothing but the next state is equal to the previous state, right? So that what we have here, the next state, if this is we call as a next state now, we have a bubble here. The next state is nothing but the previous state here. If the previous state is 0, the next state is also 0. If the previous state is 1, the next state is also equal to 1 here. Now when t is 1, j is 1 and k is 1. What is j and k is 1? What to understand by this one? By looking at the function table of this one. Anyone? What is the next state when both j and k are equal to 1 simultaneously? What is the next state? Anyone there? Rudresh DR is there? Stuti?
Sir, complement of the previous state, sir.
Yeah, that's absolutely correct, Stuti. Thank you for that, answering that one. Yeah, as Stuti said here, when j and k are equal to 1, the next state is nothing but the complement of the previous state. If I call this as a previous state now, right? As I said, it is nothing but the output is nothing but the complement of the previous state. They assume that the previous state, what we have, if the previous state is 1, if the previous, we'll assume that this is q and this is q bar, right? If the previous state is 0, the q bar will be 1. If this is 1, this will be 0, right? So that what we get here, when I say q bar, the output, the next state is equal to the complement of the previous state. If the previous state is 0, the next state will be 1. Similarly, if the previous state is 1, the next state will be 0 when both j and k is equal to 1, which is nothing but when t is equal to 1 here, right? Which is nothing but t stands for toggle. Why it is called as a toggle? Because when the t input is equal to 1, the output will toggle here because the next state is equal to the complement of the previous state when the clock input is applied. Anyone any doubts with master slave flip-flop? We studied about the master slave SR flip-flop, JK flip-flop, D flip-flop and T flip-flop, right? Any doubts with this one in understanding? Let me know. If you have any question, you can think for a while so that at the end of the session you can have the question, or else if you have any questions we can discuss now. Shall I go to the next section then? The next what we have is characteristic equation, right? We studied the master slave, the flip-flop. We know the function table. When I say function table, we know how the flip-flops will work. We know the behavior of the flip-flops there, right? When I say characteristic equation, what do you mean by characteristic equation? As I put the statements here, the algebraic description of the next state table of a flip-flop is called the characteristic equation of the flip-flop, right? This can also be stated as a characteristic equation is an algebraic expression for the binary information of the characteristic table, right? Similar, if you remember the module 1 what we had, right? We studied about the K-map, right? We have a truth table. We prepared the truth table, right? From the truth table, we try to simplify the given expression, right? With the help of the truth table, and whatever the values we have, we put it in the K-map, and with the Boolean algebra concept, we try to simplify. We look for the logical adjacency, and we try to simplify the given Boolean expression there, right? Now, similar to that, here what we do is, here with the help of the K-map, for this flip-flops, we come with a characteristic equation. And how do you come with the characteristic equation? By looking at the next state table of the flip-flop, which we call it here as the characteristic table, right? It means that the first we need to come with a characteristic table. How we can come with a characteristic table? With the help of a function table. We know the function table for a SR flip-flop. We know the function table for a JK flip-flop. Similarly, we know for a D flip-flop and a T flip-flop. Right? Now, with the help of those function table, we come with a characteristic table. In characteristic table, what we do is we give binary information to the previous state. Right? I will explain this one as we explain the characteristic equation for each of these flip-flops. Right? As I said here, the character equation is nothing but the algebraic description. How do you get the algebraic description? With the help of the next state table here. Right? Now we'll come with the characteristic equation for SR flip-flop. What is the function table for this one here? Here, if you see the difference between the function table and the characteristic table, anyone can have a look at this tables, function table and characteristic table, and tell me the difference. What is the difference between these two you see here? Now, if you see the function table, what we have, the next state is expressed in terms of the previous state. Yes, previous state, but we have not given a value for the previous state here. But when it comes to the characteristic table, what we have a value which is given to the previous state. Right? Maybe if you're unable to understand the behavior of this one, of any flip-flop here, because the function is explained with respect to the previous state here, but here we have given binary information to the previous state here, right? And the previous state we have given the values as zeros and ones here. Have you understand here? Yeah. Now how this works now here? Yes, R is 0, 0, and we have given the previous state here. Since yes, R and Q, since we have 3 inputs, 2 raised to 3 is 8. We have 8 combinations we have, right? This is 0, 1, 2, 3, 4. We can write it as 0, 1, 2, 3, 4, 5, 6, and 7 here. Right? Now what we have, when both S and R are 0, you can see here both when S and R are 0, the next state what we have, Q plus is equal to the previous state. Now what is the previous state we have? The previous state is equal to 0. So that what is the next state? It is also equal to 0. Similarly, when both are S and R are 0, the next state is equal to the previous state. Now what we have, the previous state is what we have it here is equal to 1. So that what is the next state? It is equal to 1 here, right? Everyone can better understand with the help of the characteristic table here. Similarly, what we have, when S is 0 and R is 1 here, irrespective of the previous state, the next state is always equal to 0. That's what we have. When S is 0, R is 1, which is nothing but reset state. Irrespective of the previous state, the next state is always equal to 0. Right? You can see here when S is 0, R is 1, the previous state is 1. Since it is a reset state, irrespective of the previous state, the output is always equal to logic 0 here. Right? Similarly, what we have, when S is 1, R is 0, when the clock input is applied here, what we have it here, it is set state. Irrespective of the previous state, the output is always equal to the next state is always equal to logic 1. when S is 1, R is 0, right? Irrespective of the previous state. You can see here the previous state is 0, but the next state is equal to 1. Similarly, when S is 1, R is 0, right? Since the previous state is 1, since it is Z state, irrespective of the previous state, the next state is always equal to 1. Similarly, what we have? 1 and 1. As I said here, we cannot simultaneously apply S and R equal to 1 because it is indeterminate state or undefined state. So these two states are not allowed for SR flip-flop. We cannot apply both S and R as logic 1 simultaneously. Right? Now what is the simplified expression for this one? How do you come with a simplified expression? We already studied about the K-map for 2 variables, 3 variables, 4 variables, 5 variables, right? We don't care conditions also we studied, right? Now how do you come with a simplified expression or the characteristic expression here? Here we call it as a characteristic equation. How do you come with a character equation for this one now? As I said here, since there are 3 inputs, so that how many cells we have in a K-map here? 8. 2 raised to 3 is 8 cells. How do you give the numbering? Everyone know how to give the numbering for this one: 0, 1, 2, 3, 4, 5, 6 and 7, right? Yeah, this is what the author has followed, right? If you see in a different textbook, they have different naming conventions, they have it. So that you, in some other books we have, this is 0, here it is 1, 3, 2, 4, 5, 7 and 6. Depending on the numbering also, your input also varies here, where you give the MSB and where you put the LSB here, right? Now here is S is an MSB, and R is an Q is an LSB. So that what we have, S, R and Q. And the horizontal lines, what you see is nothing but the values for the SR inputs. S is 0, R is 0. S is 0, R is 1, right? Similarly, we have both S and R is equal to 1. Here S is 1, the R is 0. And this, the vertical values, what you can 0 and 1, these are nothing but the values for the previous state, which is Q here, right? Now, looking at this one, now we have the values for this one, right? We have this as a, this is, we have just 5 minutes, just a minute. Now what we have it here, you can see just by looking at this one. As I said here, when both S are 1, it is indeterminate state. We call it as a, taken as a don't care conditions, right? So that what we have here, guess we just have 2 minutes, 5 minutes here. We'll try to wind up this one. This is 0, 1, 2, 4, 5, 6 and 7. This is nothing but don't care term, right? 6 and 7. Accordingly, we have written it here. 1 we have it here. This is 1, this is 1 and 4. So that in the decimal cells, what we have, 1, 4 and 5 is 1. Cells 1, 4 and 5 is 1. And 6 and 7 it is don't care. Now we know how to group this one, right? How do you group this one? As I said here, we should always go for maximum number of mean terms group, right? As you can here, we can make a group of 4 here, right? So that what is an expression for this one? I can see here, this is 1, 1 and 1, 0. What is the common term we have here? It is 1. Yes, here, right? It is 1, 1, 1 and 1, 0. Similarly, what we have, we can see here, we can group the mean term 1 and 5 here. So that what is the expression for this one? It is 0, 0 and 1, 0. What is the common term we have? 0 and 0, which is nothing but R bar. And what is the common here? Q is 1. So that R bar Q. So that what is the characteristic equation for the SR flip-flop we have? The next state is equal to S or R bar into Q, and we said SR is equal to 0. It means that this condition, what it says is that we cannot have the S and R as logic 1 at the same time or simultaneously, right? Everyone understood this one? How to come with a characteristic table by looking at the function table, and from the characteristic table how to put the values into the K-map and come with a characteristic equation here. Everyone? Now the one exercise I want to give is do the same. Come with a characteristic equation for JK flip-flop, for D flip-flop and T flip-flop. Right? We'll discuss of the characteristic equation for these flip-flops in the next class. Okay? Any questions you have it? If you have any questions also, you can post it in the WhatsApp so that we can discuss in the offline.